In this video, we're going to go through another step towards a more realistic simulation. We're going to start off with an assembly in SolidWorks, and the assembly is a pretty simple one, basically. It essentially is this, which is an aluminum pipe, and inside the aluminum pipe is a steel rod just bolted in there. I got a problem for you this time. Now this example, the way that I've done this, it's really just finger tight. You want to do heat? Do that, buddy. Do that. Oh, of course they can do that. Finger tight. And yeah, pretty simple. In fact, this is a classic example in strength of materials. What we're going to do is look at what happens when you heat that assembly, because the different thermal expansion coefficient of aluminum, which is the pipe on the outside, a fairly heavy walled piece of aluminum, and the internal feature, which is steel. Now, if you remember your strength of materials, you'll recall that aluminum has a very high thermal expansion coefficient, so it wants to expand quite a lot when you heat it. Steel, not so much. And so what would happen if we heat up an assembly where at room temperature the parts are just in contact, and then as you add heat to it, the aluminum is going to want to expand and the steel is going to want to restrict that expansion. Now again, if you go back to your strength of materials course, you've probably done this example. If you haven't, it's a good thing to try. Let's get to it. That's a soldering iron. Let's see how long it takes for the tip of the soldering iron to get hot. Come on, guys, I know you can do this. It's just a soldering iron, and you know what it's like. I think you can say that it's made from a casing of steel with a copper core, and the core, well, I'll get the pictures. Don't worry, I'll find you some pictures. This aluminum rod is curious because the dimensions are not showing up there, but the inside diameter is inside radius is 5 millimeters, and the outside radius is 15 millimeters. So it's a fairly hefty wall. And what I've done here is, because we can take advantage of symmetry in this problem, I've only modeled a slice of it. So it's a 30-degree slice. Now, I've also modeled the outer shell. Same idea. I've made it a 30-degree slice. And I've simulated it such that it should be aligned. I'll have to check that. I've simulated it such that it's the same slice, and more importantly, this face on the steel and this face on the aluminum are coincident. And so if we do that, then we should end up with an assembly here that's fully in contact. And then I've taken the assembly and simply saved the whole assembly as a step file. And if you do that, then you can import it directly into ANSYS. Oh yeah, for that soldering iron, I checked it out, and you know, it says on the label that it's 65 watts. Here I am in the ANSYS window, and you've seen this before. Now, what we're going to start off with is a steady state thermal problem, and I'm just going to drag that into a standalone system. So this, we could go through the steps as you have before, but before we do that, let's do another trick, which because we want to do the thermal analysis, we want to actually expand or heat up the part, then we want to see what stresses are involved with it. We can actually do a coupled analysis. Literally in this graphic, we could take a static structural simulation, and we're going to use the same engineering data, the same geometry, the same model, and the solution, in fact, from this. And if we link that, it shows up as a linked system. Now, we could also do, let's say, a transient system. And in this case, we want to use the same engineering data, the same geometry, the same model, and the same solution, perhaps, as the steady state thermal. And so that allows us to now do a transient. Now we could even go further and do a transient structural analysis from that, where we're going to share the data from there. And so now you can see that with ANSYS, we could start off and we can do all of the work in creating the conditions for the steady state thermal model and feed those into more sophisticated analyses later. So now that we've done this, I'm going to save this project as broad example. And I'm going to go to the engineering data here, and you've been through this before. I'm going to edit it, and jeez, he threw this at me. Holy smoke! I want to add from the engineering data sources, I want to add a general material. I'm going to use aluminum since I want to have a coupled aluminum and steel system. And there we go. Now that engineering data will ripple through all the different analyses that I'm going to use. I will import my geometry. I'm going to browse, and the geometry I'll import was here somewhere, heated rod assembly step. And you'll see that that geometry ripples through to all the different models. Now, since the first model that we're going to use, which is shared with all of the other solutions, is in the steady state thermal, we can open up ANSYS Mechanical. Yeah, I bet they can't figure out what the heat transfer out of it is going to be from. Oh, I bet you can. I bet that you probably know already that it's convection, and you're going to go and pick a film coefficient that makes sense for convection. And you know, if I were you, what I'd be doing is I'd be saying it's room temperature starting. And you'll see once it's done opening that we have all the different analyses that we're going to use, all shown here on the tree on the left. Now the first thing we're going to want to do, we can check that the geometry was loaded. We've got two separate objects there. The materials, we've got the two materials at our disposal. And the first thing we want to do is a material assignment. And I'm going to select a body, and I'm going to choose that body and assign it. Around it is room temperature, and then I'd let it heat up from that. And then I'm going to do a second material assignment, and I'll pick that body and assign it. And there we're finished. So we've got those two materials assigned. Oh. Now the other thing that's new that we haven't done before are connections. Now you'll see that in the connections tab that it's showing up as contacts, and the software has already identified that the model I've put in has these contact areas between the two parts. And so that's good. If in fact we had designed the parts such that there was a bit of clearance, we could still specify a contact area between those clearance areas. But for the moment, with this model, we're fine. So the first thing we need to do is the steady state thermal. Initial temperature, we're setting that up at 22 degrees. Analysis settings, it's a steady state problem. We'll just leave those as standard. Now to the solution. To here, we need to add some conditions. Now, for starters, since this is a thermal analysis and we're using the idea of symmetry, as you saw in a previous video, if we use a perfectly insulated boundary, then that does the job of simulating our slices. And so I'm just going to make these perfectly insulated. And I'll apply that. So now for the rest of the conditions, what I'd like to do here is I want to add some heat. And I'm going to add heat flow, and I'm going to do it to this top surface and this surface. And I'm going to put in, I want to put in about 200 watts perhaps. I'm thinking that I want to show heating this up a lot. And 200 watts, now this is a 30-degree slice of the full circle. So the 200 watts that I'm imagining putting into the end of this would be divided by, well, there's 12 slices. So that's going to be 200 divided by 12. Yeah, so it's something like 15. So I'm going to make it 15. So I've got 15 watts going into those surfaces. Now the other thing that I'd like to include would be some convection. And I want to pick that surface. And I'll apply that. I don't really want to have convection on any other faces, but I'm going to give a film coefficient of 10 watts per meter squared. Now for the rest of the surfaces, I'm actually going to assume that the bottom of this are perfectly insulated. I'm not going to really worry about these small surfaces here. I could, I suppose, but I'm not going to do that. So with that, now I've fully defined the steady state thermal, and I can solve that. Oh, before I solve it, I'd better say what I want to see as the output. I want to see the temperature distribution, and I'm always interested in the total heat flux. So solve. And there we have it. Now for the temperature distribution, whoa, that gets hot. So my minimum temperature is 800 degrees C, and my maximum is 1000 degrees C. That 200 watts put into this thing, it's gonna really smart. So we've got quite a temperature gradient through there. Now, because we've heated up this part so much, now we can look and see what does that mean for the structural. Now, you recall that I've imported the load from the body temperature that's just been solved. And I need to add some more conditions here because I haven't actually imported the structural elements. And really all I'm going to put in here are some supports. I'm going to have a fixed corner. I'll pick that vertex. as fixed. And for supports, I guess I want frictionless supports. And that would be this face, this face, this face, and this face. Recall that when I said with symmetry, things that are crossing perpendicular to the symmetrical surface aren't allowed. And if I have a frictionless surface there, then this part can slide on that surface, but it can't bulge into it or pull out of it. There. So that should be sufficient. And with that, I should be able to solve. Oops, and once again, I forgot to specify what I wanted to solve for. Yeah, maybe they know what the room temperature starting point is, but I don't think they're gonna figure out the film coefficient. Guys, I know you can do this. I know you can do the film coefficient. It's gonna be awesome. So I've got my equivalent stress. Now I made a pretty coarse grid, and that was just for saving time in the video. And you can see that my stresses are 10 to the 9th. Now it happens that if I look at, let's see, structural steel, whoops, the yield strength of structural steel is 2.5 times 10 to the 8th pascals. And if I look at the stress, I'm 10 to the 9th. So if I just move that down to 2.5 times 10 to the 8th, you can see from that plot that according to this simulation, I've definitely yielded this material from the thermal effects. Now the stress, it's the same. The stress is calculated for both the aluminum and the steel. The yield stress for aluminum, however, is quite a bit lower than that of steel. Regardless, we know that the aluminum is fully yielded in compression, and the steel will have yielded in tension. Now we could carry on and do the transient analysis, and that will take a bit more time. But I'll stop there because I think in one of the previous videos you've seen some of the transient done, and I think you can follow along the same process. So that's an example of using ANSYS in a bit more sophisticated way to do a coupled analysis where first you solve for the thermal, and then you can solve for the structural, and you can continue with other types of solutions that share data and share results to make the next part of the model carry on. So it's a really powerful tool, and with this, we're getting into some of the reasons why ANSYS is such a useful tool for you to have some power with. Just before we go, let's have a quick look at this model and the statistics of the grid. So if we go up to the mesh, then you can actually look at how many nodes we had. I ran this model with only 776 nodes, 175 elements, which is quite coarse. Now, I ran it separately with about 10 times that number of elements and validated the same result. The fact is that you need to, as I've said before, try some different grid sizings. For the purpose of this video, though, I kept it coarse so that it would go through quickly. Oh, and don't forget the assignment.